All right. Thanks to the organizers for having me here today. And I try to talk a little bit about how we constrain GPDs at the EAC, starting to talk about exclusive processes like DVCS and vector mesons production, and then I'll switch there a little bit later and talk about, again, nuclear PDF, impact studies that we did for the EAC, and also some nuclear GPDs and imaging with nuclei, and how we can probe saturations maybe, and then I will summarize it here. So I don't have to introduce maybe to this audience again that we started our knowledge from HERA and what the GPDs are and so on and so forth. So let me skip the introduction and we move quicker to lunch maybe. So here I just want to set the stage of what I want to talk today by mentioning the processes that we want to measure. Again, when we talk about GPDs, you always hear about DVCS. It's a golden probe, certainly, because it's clean experimentally, because you don't have complications due to the wave function of the vector mesons, and because by evolution in Q square, you can probe both quarks and gluons. So this is a very powerful probe. But certainly, when you want to do a complete GPD extraction, it's really relevant to and complementary to do also vector meson production measurements is exclusive. And yes, here you have some uncertainties on the wave function, but for instance, if you have high mass mesons by the J psi or upsilon, you can directly probe the gluons because you have here something which is produced in a CC bar pair, and it's produced by a core-gluon fusion, so it gives you access to gluons. And if you have lighter mesons like the rho, the omega phi, you can start separating the flavors. Another complementary way to separate the flavor is, of course, to measure DVCS not just on the proton, but also on the neutron. That means for a collider on deuterium or helium-3. And this is also another complementary job that you can do in extracting the GPDs. Now, what are the experimental observables? Certainly, the differential cross-section is one that everybody wants to measure, and this is really sensitive to GPD H, weakly coupling to GPD E. This is actually a way, basically, to access the imaginary part of the scattering amplitude. If one wants to access to the real part directly, the best way could be to have positrons, which is now kind of out of the canon goes of the electron-ion collider as we see it now, but this could be a direct way, and it was done at HERA to access the real part and also to determine everything which is excited right now for the GPD business. A very powerful observable at EAC, which we didn't have at HERA, will be to polarize transversely the proton beam, the hadron beam, and measure the AUT asymmetry, because this gives a good access to GPDE and good constraint. GPDE, as you know, opens the window to the spin physics, because through the GSAM rule, you can also constrain the contribution from the orbital angular momentum to the proton spin. All what makes EAC good and great is also great for imaging. So we want something which has high range in x and q square, which can be polarized, which allows you to have different ion species and high luminosity. And this is clear actually from this plot that we also show in the white paper, and shows the coverage in the phase space of an EAC compared to current facilities and near future facilities. Maybe this plot should be updated a little bit on the Richard Hayek's, but here you can see that an EAC, once you reach the full span of energy, it really connects the region where you will have data from JLab 12 down to where HERA got the vector meson and the DVCS data. This is just showing the DVCS data. This overlap with JLab 12 will be a good thing for a sanity check for an EAC. So if you overlap with JLab 12, that will release very high precision data on DVCS and GPDs extraction. Here we can actually cross-check what we are doing at the EAC. Even more relevant will be the impact if you can overlap with HERA data, because here these points are really limited by lack of statistics, lack of experimental precisions, and so on. Most of these are actually total cross-sections. And a great job that the EAC wants to achieve is to map the transition in fine beams in x-2 here in between. Right now, when people do feeds of GPDs, I'm aware at least that they do really do it for low X or high X, and they sometimes do an evolution at a region-like to move from one region to another. So having a very detailed map here in between will be really challenging, posing challenges to the theorists to describe this evolution very well, not only for DVCS, but also for mesons. Well, we did back in time, and this ended up in the white paper, an impact study with Elka, Kresokunericki, and Dieter Müller, considering DVCS alone. So what we did is to consider DVCS and its main source of background, the beta-height process, and do a full-fledged mock analysis, let's say. So we simulated the data, we did a signal extraction the same way we did at HERA. We measured cross-sections and asymmetries. We also accounted for some analysis details that minimize in the cross-section measurement the contribution from the beta height, which was kept below 70%, 60%. We also had a look to relative cross-sections. We smeared and the variables according to the resolution that we expected at that time, and the detector acceptance, and so on. We considered 5% systematics. So all this kind of detailed analysis to see what we can do with GPDs extraction from DVCS. The Monte Carlo that we used was MILU, which is the only thing at the time that we had based on a GPD model that described HERA data. It was actually used by the H1 collaboration for data measurements. Here already you can see, and this is I think also in the white paper, at lower central mass energy, higher central mass energy, how detailed can be a binding at an EAC in x-2 and t, and how really you can collect enough statistics in each beam to do a great measurement. And here is, for example, how we can constrain the height. I go fast here, and also we studied some initial state radiation that we had to take into account. But here you really see the greatness of an EAC measurement. So here is two beams, one at low X and one at larger X, 40 square larger than 10. And here, these are very precise measurements that already account for systematics, and they are actually systematically dominated already for luminosity, which is 10 inverse femtopower. If you Fourier transform these quantities, this cross-section, you already have the Proton densities. These are average Proton densities. I cannot say gluons or quarks, but it gives you the idea of the precision in the imaging that one can achieve at DAC, evolving it in x-2. So this will be a great job. Also, we considered the ANT, which again is a powerful tool to access GPD. You can see here these precise measurements again in a tiny bit in x-2 at larger and lower x. Everything is around 0 because we didn't have a prediction in our Monte Carlo for the ANT, but one is interested in looking at these tiny uncertainties that give you basically whatever is the ANT, this is the prediction, the precision to which we can measure it, which is enough to discriminate between theory assumptions. So back in time, what we did in the end is to take all this bunch of simulated data in this analysis and make a global fit together with the HERA data. So in these fits that were actually performed by Kreso and Dieter Müller, you can see that the fit that you have on the GPDs without the EAC is in purple or blue, and after you add the EAC is in orange. So you can see here, you can squeeze the uncertainty for the GPDH for the sequence, but remarkably, you can also constrain very well the GPDE for the sequence. And at that time, from that model, it was unconstrained. And also, you can improve greatly the uncertainty on the GPD H for the gluons. Again, a Fourier transform gives you directly the impact parameter imaging like this. So this is the kind of tomography that you will do in the end. Here, this shift is due to the GPDE. That was what we did back in time, and this was what entered the white paper. What is missing here is totally the inclusion of mesons, as I said before. For instance, I believe that if we include J psi and upsilon here, this will shrink to a line as well, and we can also attempt to measure the GPDE for gluons.
Do you have,
yes.
You show only H and E, but do you have HT?
No.
Okay. So
no. And also, you need to put the scalar mesons for this. So this is an unfinished business in a way of speaking. But it gives you already an idea of what actually you can do. Also, I must say that all these kind of like fits of the GPDs right now are very model dependent. So you need, it could be interesting, for example, to compare different predictions and do the same. But yeah, there is work to do. For instance, here is a summary. This is actually taken from Marcus Deal thesis, and he was the first one who proposed to use mesons for do flavor separations, and each meson to what is related, what you can actually access, and of course, like using deuterium and helium-3 polarized will be also a complementary powerful probe.
Salvatore,
yes.
Can I ask a question?
Absolutely.
So there's quite some discussion, as you know, to what extent we really understand shape side production in a collinear framework. So apparently the formalism is not so stable, especially if you go to higher energies. I'm just wondering if this statement of this very narrow profile, we can actually keep making this today.
This is just a Fourier transform of the cross-section, right? So it doesn't include any theory prediction. So this is just to show what was done here basically is this. So you measure the J psi, simulate a measurement at an EIC of the differential cross-section, and you Fourier transform it, and it gives you, basically if it's a J psi, I can safely assume this is an average density of gluons. And you can see how precisely you can constrain these even at large impact parameters. So this can
I really make that statement? I mean, if whatever leading order next to leading order gives very different results. I mean, from basically going from the data really to right away telling me the profile of the gluon distribution. It's not so clear to me.
Okay, it's not clear if this is.
I mean, if you assume you have a leading order framework, you can do that.
Yes.
So as Les Szymanowski and co-workers have shown, I mean, it's not at all stable to higher order corrections. You could not even just call it correction. It's a huge change. So,
I agree. This is more a challenge to the theory. Say. So it's like here we were just trying to prove the experimental precision. But
I mean, in general, I really started wondering whether, let's say, relatively strong statements about the J psi channel that were made in the old white paper, as we speak, we can still maintain that.
Yeah, for the flavor separation, you limit to black melons or DVCS. How about the scalar melons, peons, times, where they have?
Yeah, those should like be used to for constraining, for instance.
I'm always a very bold person to believe that a phi can help you learning about
this is what I say. It's from Marcus.
No precedence at all in any setting, inclusive whatever. So I don't believe it for 1 second.
So we can use phi for constraining.
No, those will still work. They will work. But either way, I mean, yes. Yeah. I think the message, I think you need to have a combination of factoral meson, scalars too.
The
interpretation as a gluon is you can argue that. But think you only want to show the quality of some data.
But at the end of the day, we say we can kind of map out the gluon profile with accuracy. So right now with the shapes, I am, at least the numerical results I've seen, I'm concerned.
But do we believe that with the combination of the data, I mean, at some level, the question is always, it's difficult to predict what in the end your uncertainty will be. There's too many questions, I think. So my guess is just, if we want to look at it, we should just be careful that we don't, I mean, the danger is always if you make the statement too strong in the text. I mean, I think that's what you're pointing to. Some level, the figure is still the figure. It might not be the gluon density.
Yeah, that is. If the strong statement is that we call it
Many figures.
we can call it the Fourier transform. Or,
No, but the hex on the axis is correct. I mean, what's next to this, you can argue.
yeah. Okay. Yeah.
Points.
Point taken.
I don't
I don't know how to fix it.
I don't know how to fix it.
Precise, but what is it?
I don't know how to fix it.
So, but in the end, you could extract the GPDs out of it. So you're not just doing a Fourier transform but the cross section, right?
So, Andreas, I think maybe, I don't know, I mean, so I want to come, so if next calculation really changes the T dependence, that I will worry about. But they didn't show that the T dependence will dramatically change after you take into the next calculation line. So for that, maybe I think it is safer. I think it's safe to say that.
But how the T dependencies are largely parameters is also one topical discussion.
Yeah, I know, but
They are even adopting those exponentially up to
their calculation not for that.
Yes.
I mean, they are just calculating total cross section
Yes.
at differential cosine T equals 0. So I think maybe it's okay, right?
I don't know. I'm worried about the fact that I have a framework to calculate the total cross section and the perturbative calculation, and it doesn't converge actually in a large kinematic region. I mean, this is what the calculations show.
No, but we've seen a lot of calculations that are not next order. By the time we actually have the data, we might we have made some progress on that side as well. We will not be at the leading order anymore.
No, I mean, NLO exists now, and people look at including basically small X resolution effects. It doesn't look that stable. I mean, I'm optimistic that some of the
and we had a lot of these discussions with Igor and others to move to NLO and see if you can stay put. That's why I say like it's a challenge to the theory in the end, because right now you will not have a means to describe in all the phase space and NLO Masons using JPSI and other Masons, or but so.
I mean, what happens with open chart? Dimension?
I don't know.
Yeah, how about
No, that doesn't work. You need the two gluon exchange. I think you need the EXI, isn't it, for that? Is that right? If you look at the diagram they use for the interpretation, I think you need the EXI.
And if you produce a dimension, it will never be exclusive.
It won't be like exclusive. So that's the problem. At least for this interpretation, I believe.
And you cannot do
believe.
open charm.
No, but the other way is that the open charm works, but not the way this is done, I think.
You
But
cannot
I
have
think
open charm and explicit process.
But it sounds to me we just have to be careful. That at some level we can't hinge all our arguments based on just the excited. That's what it sounds like. Just have to be careful how we phrase it.
What you saying produce 2Ds with the last two?
Do you do you?
That's what you say. So,
That would work.
All right, so yeah, back on this review, this is also a study for Upsilon, was done by Zenedine and people from Temple. I take this light directly from the users group, and it actually shows that we can actually measure upsilon very well here, assuming it's a high heavy meson, so we assume here like 10 times more the luminosity that was assumed here for the J psi, and you can have actually very good statistics in each of these beams, and do the same Fourier transform that shows, as usual, that you have these tiny errors. This is kind of like, instead of the J psi that was always in the DVCS, we always say like high or low energy, this is actually done at an intermediate energy. So, but it's fine, because if you go to the top energy, then going lower in X, actually you have the benefits that you have 3-factor times more cross-section that compensates somehow the drop in luminosity that you may have at highest energy. So you can measure J psi in the whole range. Where you want to measure it for the GPDs extraction at an ENC. So we did also a workshop recently on these topics at Stony Brook, and then it's agreed that basically we need to put the community now together. It's timely to put the community together to assess these problematics. And what we actually want to consider is to turn the Proton project framework, which is something proposed by Harvey, Yakub, into something like similar to XFitter, where you can put models and then you can actually do some fittings that gives you an idea, for example, of impact studies and things like this. So we plan to get together again end of January, I guess. It's not announced yet, in Warsaw, and work hands-on with also people involved like Fazio or Peter, and I think like advice. So we'll try to work on this, because certainly we need to make some progress in the community before NESC starts to ramp up. Few words about the Raman pot spectrometer, which is actually a crucial component to do this kind of studies. Or we need to measure directly the proton in the final state, and we need to do it with an acceptance which is close to 100% if we want not to waste all our great luminosity into an acceptance problem. And this will measure precisely the final proton momentum, and also it's a very clean way that we use Detector to select diffractive events. This is the ratio between the longitudinal momentum of the scattered proton and the beam. And if you are around 1, this is a very clean way to select diffractive events, and you don't have proton dissociation on the ground in this case. So very crucial component, as you see here, and this energy is typical of DAC. If you have a Raman pot spectrometer with an aperture in theta of 10 millirad, it catches basically all the protons. It fits designed properly in also.
So Salvatore, I mean, I agree with you, we need Raman pots. I'm always worried that people just portray it like this, because in reality, on one side of your slide, you have 35 milliradian. On the other slide, it's less than 10 milliradian. So we always don't need Raman pots, but we also need detector beyond the Raman pots to cover this whole thing.
If you want, yeah.
Well, we want to have 35 milliradian, isn't it? So,
yes, if you go to lower energies, yes.
That's well, you too. Is that you have it there too?
Oh, so here the Raman pot should cover totally these two regions, right?
Yes, I agree with that, but you have there 35 milliradian. That's all I'm pointing to. I agree with that figure.
Oh, where is it?
On the whatever, right, on the top.
That's
all I'm pointing to.
All right.
Then we need something beyond the Raman pots.
No. Yeah, it's like for the Raman pots.
No, I agree with you that. I agree with that.
This kind
Yes, that is in the main detector.
35 is already.
No, but there is a region between 10 milliradian and 35. We want actually figures. That's all I'm pointing to. 35 is in the main detector. I agree with you. But there's a region in the middle. Yeah, that's all I'm pointing to. You don't only want Raman pots in the main detector.
No. All right, so
you have this large acceptance from both J.
I agree with you. It's the way it's presented. I agree with you.
Yeah. Sorry. It's like check the number.
Just on the safe side.
So yeah, we need just a quick study back in time also to see what is actually that you lose or gain if you lose acceptance in PT, for instance. So you can see here that the same plot. Okay, this is the white paper basically. The cross-section of DVCS and its Fourier transform. If you lose acceptance at low end of PT, basically this becomes less precise over the Fourier transform with errors bar. And if you lose something at a large side of PT, you blow up a little bit here in the low impact parameter place. We also played a little bit this game with the luminosity range. So if you instead of collecting 10, you assume you collect 1, of course you lose precision here in this region. This tells you that we really want to achieve a luminosity to the point that we are systematically challenged, and this happens for DVCS around just before 10 inverse femtobarn, but you can start doing some impact physics at the beginning, like the first months of data taking already by accumulating a less luminosity sample, let's say. Few words on the nuclear PDFs then, because we also studied the impact that we have in those. Let me skip here maybe the introduction and just jump and say that we used at that time the INT-18-3 last year, which was the state of art. It's from the Vasquila and Carlos Delgado group. So here they replaced EPS09 by adding also port flavors to it and also the latest LHC data. Actually, we went beyond this, and since we want to assess the impact of gluons, and it was mentioned in the previous talk that here they have a very stiff parameterization. So you see that here it goes down in X like flat, because it's actually that the gluons are constrained by the parameterization itself. So they released a little bit the parameters for the gluons only at low X, and they call it EPS16 just for the purpose of these studies. And you can see here how now it's like flexible to vary at rho Q squared. So we did a full analysis again of the data that the NEAC can measure in the inclusive. This is the reduced cross-section. You can see here very precise errors. We consider 3% systematics. To better appreciate the uncertainties, let me zoom in and just show 2 different examples at higher and lower Q square, compare with the theory knowledge, and you can see that in both cases you have very good improvement versus current knowledge. This already assumes the systematics update literature, and actually we are systematics challenged in this measure. We assumed again 10 inverse femtobarn. Here, the both lower end plot basically shows the comparison of these error bars in the experiment compared to the size of the theory. You can see that you can have a remarkable impact at low X, but also at intermediate and large X versus current knowledge. Only for the inclusive, we also studied some radiative corrections. Maybe I don't have much time now to go in details, but also extracting the FL structure function, which requires you running at different energies. At least we consider 3 different energies. All right. So basically, even when we've been in energy and in Y plus here for the FL extraction, if we collect this case, we assume 4 plus 2, that means makes a total of 10 integrated femtobarn luminosity. We are really challenged by systematics to the fact that here we plot the ratio between statistical uncertainty and total uncertainty. You can see that here it's basically the statistical is 1 to 3% unless you go to very high Q squared. A novel probe which will make a difference at the AC, and it was mentioned in the previous discussion in the previous talk, is to measure charm. We can do a very nice job if we carefully plan the detector to measure the charm at an EAC. For instance, we consider these charms measured out of chaos coming from the decay of the D mass produced. This is nicely tagged if you require a displaced vertex, that here we assume between 0.1 centimeters and 3 centimeters. And then you need to have chaos ID basically everywhere in your detector, in the central region, in the forward, and in the rear region. Here we assume BEAST, which is the model detector of DNL. I assume that this doesn't greatly change if you use carefully designed other detector configurations. You can see here, for instance, that if you require displaced vertex, as you move from the nominal vertex, everything is basically that survives is the charm. And here is basically the rapidity coverage and the momentum coverage of the decaying canons that are completely within the reach of an EIC detector. We studied the background, and basically we concluded that will be not significant, and also the efficiency that, okay, in our model detector was around 28%. Well, when we do now the feeds using the INT-18-3, including the DIS data that we simulated, you can see the orange band is after we include the EIC simulated data. You can see how we squeeze the uncertainty. Here is a lower energy EIC and a higher energy EIC. So we have roughly, but this is with a grain of salt, of course, a mistake, and like a factor to squeeze in the uncertainty for a lower energy, and at low X, of course, if you have a higher energy, you constrain even more. This is just for a DVCS simulated data, but if you add the charm, then you do a great job at large X. And this is basically, it doesn't depend much on which energy you're running the machine. You just have to produce a decent amount of charm rate, which will be produced easily. And then you can really have an impact to the point of factor 6 or more in the knowledge of gluons at large X. This is also confirmed by another independent study from Christian Weiss and people at JLab, that they use EPS09 in this case. It doesn't matter much in this region. This is a zoom at large X. And again, they find the same conclusion. It will be a remarkable job how to measure the charm at the DIC, how we can constrain gluons at large X. Another thing is the FL, and here is E-gold FL that we simulated. These are the various FL that you can measure with a lower energy or a higher energy AC, both together compared with here. And here I make the point that is also what this is one of the impact studies, the impact areas that an EIC will have versus HERA, because this is basically compared to what HERA measured for the FL, and again, we did for E-gold, we are now studying for EP, and also for EP, like for free protons, HERA will have a large impact. EIC. So this is basically what is left to do using electroweak and using deuterium and this kind of reactions for lighter nuclei. Imaging is something which will be very useful for heavy ions as well. It's kind of a greenfield right now. It's just starting right now. The people are starting to work right now on nuclear GPDs, let's say, but there is no reason to doubt that the nuclear modifications will impact the GPDs too. And the way you do this is similar to what you do with the free protons. So you just do produce in EA interactions these vector mesons or exclusive processes, and do a measurement, for instance, of the cross sections. Here you have to separate the incoherent from the coherent, and this can be done experimentally with the ZVC calorimeter in the forward region, together with Roman pots that can be the fragments and so on. So here, for example, the coherent part can probe the shape of the black disk. The incoherent is something to what is called the lumpiness, so they are both a useful thing to measure. Since we are talking about heavy nuclei here, you may expect, if you are close enough to the saturation scale, to see some effects on saturation, and especially some probes like the Phi are more sensitive than others to the saturation, and this is like a simulation that is done with model containing saturation in white or not containing in blue intensity difference. But also the light nuclei will be very interesting in this case. The deuteron, for instance, and the helium Phi is also interesting for the flavor separation in a free proton, as I say, and also for spin studies, because the spin of the helium-3 polarized, for instance, the neutron spin dominates here, so it kind of helps you study the spin of neutron and proton together. Yeah, so let me conclude then basically on the detector requirements. If you want to do very nice exclusive measurements, you need like a detector which covers all the region of zero rapidity, let's say between minus 0.5, 4.5 to 4.5, and you should have equal coverage of calorimetry and tracker. You need very good Raman port acceptance or whatever you have in the forward region. You need a 0-degree calorimeter if you really want to get to the breakup with the EM. I will just leave the summary here maybe. Just want to point out that for the PDFs, this is really systematically challenged. So this will be a very high impact year one physics. So we don't really need to collect much statistics for the nuclear PDFs. What we need to understand is our detector. And for the GPDs, there is a study done in the DVCS, and what we need to do is now to do vector mesons and study GPDs in
Any questions?
What do we know about the GPD?
nothing. Yeah,
Or for Proton?
nothing or close to nothing.
Just very difficult measurements.
Because I keep listening from the latest people that the B or the GP is very small somehow.
Yes. Yeah, the size, the magnitude will be actually this is one of nice things that one will try to do. Maybe like to have a rough measurement that really gives you the size or at least an idea of the magnitude of GPD if you do it in ultraviolet conditions for the J side production, and then you need an EAC to pin down.
Did you ever have
No, the problem is that it's small, so the only way, I think the most sensitive way probably we can get there is by using some transverse polarized target and DVCS on time like on the schedule Mason production. So the problem is that there's no difficult measurements, so no, not really. There are some plans, but still.
I remember there's some prod you guys have. I don't know if maybe you are not involved. JU constraint.
That's correct. That came from the Deuteron data. So since that what was done there was a combination of Hermes data and DVCS on the Deuteron. And I don't remember that after we redid DVCS on the Deuteron yet.
No, but I mean, I think the idea is to use the DVCS on the neutron to get to E because
So I mean,
there is
the
a F2 term, and so on the neutron it's easier. But,
so that I think comes next year. The DVCS on the.
I remember this data on this actually.
That's from the old data. That's the old data. That's correct. You're correct.
I haven't shown this prod to many people that this really bright future.
Yeah, the problem is just that was from 6CV and we haven't done it till next year. That's for next year for the DVCS. For that experiment you talk about is next year. But then the bigger sensitivity would be if we start doing measurements with transverse polarized targets, but those are different.
I remember that Tony Thomas was trying to kind of, push his agenda on his model called OBM Momenta. He showed his calculation with JUJD or LULE, right? And compare with your JI.
That's right. From lattice and then orbital. That's correct. That's the idea.
But so from that, you definitely have to have E.
Yeah.
Okay. So it's not actually, we don't know anything about E. Actually, we know. Yeah, we don't know how precisely.
Exactly. So what we know is indeed from the old DVCS on the Deuteron. Okay. Anyone else? Question? Andreas?
Probably a very naive question. Is there any chance to measure the polarization of the recoil proton?
Yes. But for the one, yeah. I mean, I've always been contemplating, but that's for semi-inclusive, that somewhere you can even have polarization if there was no polarization at all. In principle, we can, but you can only normally do it in a small piece of phase space. So we can, in principle.
We also looked at it, yeah, it's like.
So maybe the question is,
Double scalation.
what do you have in mind on layers? Well, I mean, I didn't run the applicated work that a few years ago we argued that for the GPD of the gluon, you could have a scenario that E of the gluon is large, but the typically quoted transverse single spin asymmetry, as you observe, is small. And to kind of overcome this difficulty, we could actually look at liquid polarization.
And this is for the DVCS
for shape slide
or
reduction.
the shape cycle.
So I don't know if there's. I know that people at Jefferson.
The point is that you need
for the form factors.
You need to do this on an event by event base. Or how do you do this? Because you
Recopolarization?
yeah, the repolarization of the scattered proton.
So what we're doing is statistical, isn't it? You essentially put a
Yeah.
polarized proton, a slab of carbon, and you look at the spin-orbit force. So you look at the left-right asymmetry.
So you will have to collect some data, and then
You would have to have a lot of data, that's right.
So this is the kind of polarization you need, right?
Yeah.
So an average polarization of, like, let's say, all the statistics of 2000.
I mean, it's similar to what you guys did for the F2 form factor, right? And
Yeah, we have either use carbon or use honey. Use orange.
But the typical rule is more or less that those things are going to reach you 1–2%. So you need to ship out the statistics to do it. That's why I asked.
You will have, after you collect the data, it is the main point.
So normally we try to polarize target because it gives you better feel.
You mentioned the diffractive structure functions at some point. So
This is all diffractive.
but so can you measure also rapidity gaps? Association
You
with
can measure rapidity gaps. If you have Roman pulses, also that you don't need actually to measure a rapidity gap,
but
in the sense that
but
you can tag diffraction in the way I said, like looking at the XL peak, for instance. This kind of. This was alternative Altera to use a rapidity gap for tagging diffraction.
okay, so you're not using okay. I see.
But certainly, if you have a rapidity gap, otherwise it's not a diffractive.
Both should be done.
They both should be done and both should be cross-checked. And this is why we want in most of every, let's say, detector design a colorimeter forward, like hadronic colorimeter forward.
Yeah, because the difference is also dissociated proton, for instance. So yeah, expects to be a difference between the rapidity gap and
but this dissociated proton, you don't have it.
which is not well understood also.
Yes.
So besides diffractive F2 or diffractive FL,
That you will need a rapidity gap.
so you will have also diffractive jets. So
Yes. And they actually do prop for the Wigner function, as we discussed earlier. Right? So yeah, that will be a hot topic too.
Anyone else? Thanks, Salvatore, again.
Thank you very much. Just on time. For once.
you need